Assalamu alaikum good people. Here I am with another video. In this video I will show you an AC circuit example of maximum average power transfer theorem. Determine the load impedance ZL for maximum average power transfer and the value of the maximum average power delivered to the load impedance ZL. This is our given circuit. In this circuit we have this load impedance of ZL. We have to find the value of ZL for which the maximum average power will be transferred to the load impedance ZL, and we also have to calculate the value of that maximum average power that will be delivered to the load impedance ZL. From maximum average power transfer theorem, we know that a load impedance ZL receives maximum power if the value of that load impedance is exactly equal to the complex conjugate of the Thevenin impedance of the network, and the value of maximum power that will be delivered to the load impedance ZL in that case will be equal to magnitude of Thevenin voltage square over 8 RTH. Here this RTH will be the real part of ZTH prime. These are the steps I will follow to solve the circuit for maximum average power transfer. At first we have to remove the load impedance ZL and find the Thevenin equivalent for the remainder of the network. At first I will separate the load impedance ZL from the network, and this network will be a two-terminal network. From Thevenin theorem we know that we can convert this entire network to a single impedance ZTH, and we can calculate the voltage across this A and B terminals, which is known as Thevenin voltage. So if I calculate VTH and ZTH, that will be the Thevenin equivalent circuit for this network. Okay, while I will be calculating ZTH, I will replace the current source with open circuit and voltage sources with short circuits. So at first we will remove or separate the load impedance ZL and replace the voltage sources with short circuits and current sources with open circuit. So our circuit will look like this. We replace the current sources with open circuit and voltage sources with short circuit, and we will calculate Thevenin impedance with respect to this A and B terminals. Okay, this was the resistance of 4 ohm, and this was the inductance with inductive reactance of J3 ohm, and this was the inductance with inductive reactance of J2 ohm, and this was the resistance of 3 ohm. Now see, you will see this is our A terminal and this is B terminal. Let's say this is also B terminal and this is C terminal. With respect to this C and B terminals, you will see this J3 impedance will be in parallel with this 3 plus J2 ohm impedance. So in this circuit the Thevenin impedance ZTH will be equal to, initially this J3 and this 3 plus J2 impedance will be in parallel. Their equivalent impedance will be in series with this 4 ohm. So here I will get 4 plus equivalent parallel impedance of these two. Here this will be equal to 4 plus J3 get multiplied with 3 plus J2 over 3 plus J2 plus J3, which will be equal to 4 plus 0.794 plus J 1.68. So in this circuit the Thevenin impedance ZTH will be equal to 4.794 plus J 1.68 ohm. So this is our Thevenin impedance. So this is our Thevenin impedance. After calculating ZTH, we will calculate the Thevenin voltage with respect to the same terminals. To calculate the Thevenin voltage in a circuit, we can use mesh analysis or super mesh analysis. We can use nodal analysis method. Sometimes superposition theorem works good. Sometimes simple application of Kirchhoff's voltage law or Kirchhoff's current law in the circuit works pretty good. Sometimes you need to use voltage divider rule, current divider rule. Sometimes you have to use source transformation theorem. So you have to find out which method is suitable for that specific circuit to calculate VTH. Here in this circuit we have total 3 sources, okay, this VS1, VS2 and this IS3. When we have to solve for currents or voltages in a circuit, I always try to avoid mesh or nodal analysis in case of AC circuit. Because when you have to calculate the currents using mesh analysis or the voltages using nodal analysis, you will end up with system of linear equations. In which you will get complex numbers as the coefficients of either voltages or currents, which is very difficult to solve. That means you have to use matrix method to solve for voltages or currents, or you have to use Cramer's rule to solve for voltages and currents in the network. Therefore you have to use your intuition and find out which method is used for that specific circuit. In this circuit I will proceed with source transformation theorem to simplify the circuit structure, and finally I will apply Kirchhoff's current law to find the Thevenin voltage. Okay, now see, source transformation theorem states that if I have a voltage in series with an impedance, I can convert that to a current source, and I have to place that impedance in parallel with that current source. With this VS1 I have this impedance in series. With this VS2 I have this impedance J3 in series. Let's say I am denoting this branch impedance with Z1. Here Z1 is equal to 3 plus J2 ohm. This branch impedance is Z2. Here Z2 is equal to J3 ohm. Now see, using source transformation theorem we can convert this voltage source to a current source. Let's say I am denoting that current source with IS1. IS1 will be equal to VS1 over Z1. Here VS1 is equal to 12 with phase angle 0 degree, and Z1 is 3 plus J2. IS1 is equal to 3.33 with phase angle will be minus 33.7 degree ampere. Okay, what will be the direction of this IS1? See, VS1 has positive terminal in upward direction and negative terminal in downward direction. So VS1 should supply current in this direction. To maintain the same current direction, the direction of IS1 will be in upward direction. I can also convert VS2 to a current source IS2 using source transformation technique. IS2 will be equal to VS2 over Z2. Here VS2 is equal to 6 with phase angle 0 degree, and Z2 is equal to J3, which will be equal to 2 with phase angle minus 90 degree. See, VS2 will supply current in this direction. To maintain the same current direction, the direction of IS2 will be in upward direction, and I will place Z1 in parallel with IS1 and Z2 impedance in parallel with IS2. Okay, after converting the voltage sources to current source and placing the impedances in parallel with corresponding current source, I will get a circuit like this. See, I placed is1 in parallel with z1, is2 in parallel with z2. This will be the first transformation of the network. Now see, if this is a terminal, let's say C terminal, and this was our B terminal. Within this B and C terminals, I have two impedances connected in parallel. This is Z1 and this is impedance Z2. As they are connected in parallel, their equivalent impedance will be Z3, which will be the equivalent parallel impedance of Z1 and Z2. That will be equal to Z1 into Z2 over Z1 plus Z2. That will be equal to 0.79 plus J 1.68. That means I can replace Z2 and Z1 with a resistance of 0.79 and an inductive reactance of J 1.68 ohm. Now see, in this direction IS is supplying current at node C. In the same direction IS2 is also supplying current. So I can merge the two current sources to a single one. That means IS4 will be equal to the phasor sum of IS1 and IS2. Here IS1 is equal to 3.33 phase angle minus 33.7 and IS2 is 2 phase angle minus 90 degree. This will be equal to 4.75 with phase angle minus 54.25 degree ampere. So if I replace the current sources with a single current source IS4 and the impedances with a single impedance Z3, I will get the second transformation of the circuit. This will be our circuit. Okay, now see, this was our C terminal, this was our C terminal. I can further simplify this circuit by using source transformation technique. That means I have this IS4 in parallel with the impedance Z3. I can convert this IS4 to voltage source of, let's say, Vs3 using source transformation theorem. Vs3 will be equal to IS4 into Z3. Here IS4 is 4.75 phase angle minus 54.25 degree and Z3 is equal to 0.79 with imaginary part of J 1.68. Sorry, J 1.68. This will be equal to 8.8 with phase angle 10.57 degree volt, and I will place the impedance Z3 in series with Vs3. Now see, what will be the positive side of Vs3? IS4 is supplying current in this direction, so the positive terminal will be in upward direction and negative terminal will be in downward direction to preserve the same current direction in the circuit. So this will be our circuit. Now see, from this point to this point I have 4 ohm and this 0.79 ohm connected in series. So I can reduce this impedance to a single impedance of Z4, which will be equal to 4 plus 0.79 plus J 1.68. So Z4 will be equal to 4.79 plus J 1.68 ohm. So our circuit will look like this, and from this point to this point impedance is Z4. Now see, in this circuit, let's say this is our node 1. In this node 1 we have node voltage V1. V1 is exactly equal to the Thevenin voltage of this network, and this will be our, let's say, reference node. This reference node will have a voltage of V0 equal to 0 volt. I will apply Kirchhoff's current law at node 1, or I will use nodal analysis in node 1. See, the current is entering from this direction in node 1. As we do not know the current that is flowing through the impedance Z4, so the current will be outgoing in this direction from this node 1. So if I apply Kirchhoff's current law in node 1, I will get entering current is equal to 3, phase angle will be 10 degree, and the leaving current will be equal to V1 or VTH minus this VS3 over Z4. VTH minus VS3 over Z4. So here you will see VTH will be equal to 3, or VTH will be IS3 into Z4 plus VS3 or this will be equal to 3 phase angle 10 degree get multiplied with 4.79 plus J 1.68 plus 8.8 with phase angle 10.57 degree. So in this circuit the Thevenin voltage will be equal to VTH, which is equal to 23.73 with phase angle 22.48 degree volt. So in step number 2 we can construct a circuit like this, in which the Thevenin voltage VTH will be equal to 23.73 with phase angle 22.48 degree volt. In the circuit ZTH is equal to 4.794 plus J 1.68. Okay, the complex conjugate of Thevenin impedance will be equal to ZTH prime, which is equal to 4.794 minus J 1.68. See, from maximum power transfer theorem we know that a load impedance ZL receives maximum power if the value of ZL is exactly equal to the complex conjugate of the Thevenin impedance of the network. So if the value of load impedance ZL is exactly equal to ZTH prime, or 4.794 minus J 1.68 ohm, our load impedance will receive maximum average power from the network. Okay, now see, we can compare this load impedance with standard impedance equation, R minus J X. Here this R will be RTH and this X will be XTH. This R is the real part of JTH prime and this XTH is the imaginary part of this JTH prime. Here RTH will be equal to 4.794 ohm. Now see, we calculated ZL, and the maximum average power transfer is equal to the magnitude of Thevenin voltage square over 8 RTH. Here this VTH has its magnitude of 23.73. we will take that square over 8 RTH. Here RTH is 4.794. This will be equal to 14.68 watt. Okay, the value of PL max will be 14.68 watt, and the value of load impedance should be equal to 4.794 minus J 1.68 ohm to receive the maximum average power from the network. And if I compare this with RTH minus XTH, I will get RTH is equal to 4.794 794 and xth equal to 1.68 ohm. Okay, that's it. Thank you.